Today we're going to be doing some more Calculus 2 practice problems, focusing on integrating the natural log function. So first we're going to be looking at finding the indefinite integral using u substitution. I made a whole video on u substitution, but these examples in particular are going to integrate to the natural log function. So remember, we always start finding the inside composite function. In this case, it's just the entire denominator of this function. And this works out perfectly because our du function would be 2x dx. And notice that on the top we have a very good part of that. We have the x and the dx. So all we need is the 2. We can just put it there and account for it with a 1/2 out front using the constant multiple rule. Then we can make the substitution. This turns into 1/2 of the integral of du over u. Now this is the form we're always going to be looking for, du over u, because when you take the derivative of the natural log function, you're usually left with just u prime over u. So this is the integrating version of that. And what this is going to turn into is 1/2 natural log of the absolute value of u plus c. There's just an absolute value sign because it is able to double the domain. And finally, we just plug back in our function of u, and that's all for the answer. And on this problem, it's a little bit different at first because trying to make a u substitution right away won't work, because first of all, du always has to be on the top. So for us to call the top u, that would mean du would be on the bottom, so it's not quite going to work. So what we're going to do instead is just notice that we could just simply divide the two or separate them into two different fractions. So we could just call this the integral of x squared over 7x dx minus the integral of 7 over 7x dx. Now, the first one, we don't even need a u sub. We can just cancel one x on top and one on the bottom and take out the 1/7 constant, leaving with just an x dx. And the second integral, when you cancel the 7's, it's going to leave you with just 1 over x dx. Finally, we'll just do a power rule on the first one, where we add 1 to the exponent and multiply by the reciprocal of that number. And then here we have that du over u, or dx over x form, where it's just going to turn into ln of absolute value of x. Of course, there's the constant. So finally, we are left with 1/14 x squared minus ln of x plus c being our final answer. Then we move on to examples with something called change of variables. And they give us the hint that u should equal the entire denominator. And the reason that they call it a change of variables is because, you'll see, when u is equal to 1 plus the square root of 2x, the du is, the derivative of 1 plus 2x, which is 1 over the square root of 2x times 2. And that 2 and the 1/2 will cancel. We also have a dx. The reason why we call it a change of variables is because we're going to solve this for the square root of x, or the square root of 2x, which is equal to u minus 1. And what we can do is plug that into our du equation. Now we have du equals dx over the square root of 2x, except now it is u minus 1. And when we do that, we can solve for what dx is. Dx equals the quantity u minus 1 times du. Now we're able to sub out all of this and the dx into a much simpler integral. So let's see, this is going to turn to the integral. Just a dx on top is a u minus 1 du, and on the bottom we have u. Now we could split this into two integrals and call it 1 du minus the integral of 1 over u du. And as you can see, this one on the right is going to turn into the natural log function. But the one on the left, integrating just 1 with respect to u, turns into u. Integrating 1 over u turns into the natural log of the absolute value of u. And of course we have that plus c. Finally, we're just going to plug back in our function of u, which was 1 plus the square root of 2x minus the natural log of the absolute value of 1 plus square root of 2x plus c. So this is our final answer. And it is worth noting that we could combine this 1 and this constant into another constant to finally call the integral the square root of 2x minus the natural log of the absolute value of 1 plus the square root of 2x plus like that new constant c. So that is our final answer. We have another example here where u is again going to be the entire denominator. So u is equal to the square root of x minus 3, which means the square root of x equals u minus 3. And du is 1 over 2 square roots of x dx. But we know what the square root of x is. It's u minus 3. So du equals 1 over 2 u minus 3 dx. And finally, that means that dx is equal to 2u minus 3 du. So now we subbed out this, and we subbed out this, and the square root of x is equal to this u minus 3. So let's write it as the integral. The square root of x is just u minus 3. dx, we said, was 2u minus 3, all over that denominator u. So the 2 can come out, and then we have u minus 3 squared over u. And actually what we're going to do is just fully distribute that into a u squared minus 6u plus 9. Or you know what, this is a plus 3, which means this is a plus 3, and this is a plus 3, and this is a plus 3, and this is a plus 6, and a plus 9. So these are plus 3's as well. That's all over u, and of course we have that du. So this turns into 2. We can split it up into 3 integrals. The integral of u squared over u du, and the integral of 6u over u du, and the integral of 9 over u du. It's equal to 2. The integral of u squared over u is just the integral of u, which is 1/2 u squared. The integral of 6u over u is just the integral of 6, which is 6u. Finally, the integral of 9 over u is that natural log 9 ln, the absolute value of u. Right, and then we have a plus c. Our final step is just going to be plugging back in the function of u. So it's all equal to, and we could also distribute that 2 into, so like the 2 will cancel the 1/2 and just make a u squared. U is the square root of x minus 3. So it's square root of x minus 3 squared plus 12 square root of x minus 3 plus 9 natural log of the square root of x minus 3 plus c. And when we distribute the 2 to that 9, we should get 18. Okay. So this is the final answer. Moving on, we have some trig integrals. you might say, where does the natural log function come in? And we'll see, because we haven't learned the integral of cotangent, or in this case, tangent. We know the integral of sine, cosine, negative sine, and negative cosine, but we haven't learned tangent, cotangent, secant, or cosecant yet. So we're going to have to do this without knowing that formula. What we could do is first get rid of this compositeness, like we always do with u substitution. So u is going to equal theta over 3, and du is going to equal 1/3 d theta. So in order to make that substitution, we want a 1/3 in there for the d theta, so we're going to put a 3 out front. Now we have 3 integrals of cotangent u du. And where the natural log comes from is when we rewrite cotangent as cosine of u over sine of u du. Now you can see that we have a derivative over a function. So if we make another substitution, call it w, like a double u substitution, w is going to equal sine of u, right? And dw happens to be cosine of u du. That works out perfectly, because now we could rewrite this as 3 integrals of dw over dw, which we know turns into ln of the absolute value of w, plus c, right? Except we have to plug back in our function for w, which was sine u, and we have to plug back in our function for u. So it's 3 ln the absolute value of sine of theta over 3 plus c. That is the final answer. Okay, moving on to this question. We haven't learned how to multiply, or a product rule for integrals yet. We haven't learned that yet. That'll come in a few weeks in Calc 2. But what's going to happen is when we make that u sub for the inner composite function, like we always do, it takes care of itself, because the du is the derivative of e to the negative x, which is negative e to the negative x dx. So we're able to get rid of this e to the x with the du. So this e to the negative x and the dx, and we also need another negative, so we're going to put that negative there and account for it with 1 out front. Now these double negatives turn the whole equation positive, like we started with, so we did not change the value. Now we have the negative integral, and like I said, this and this and this negative all make our du, and we just have tangent u. And as you might guess, doing the integral of tangent is the same as doing the integral of sine over cosine u du. Now if we do that double substitution, so when w equals cosine u, dw equals negative sine u du, derivative of cosine is negative sine. So we're going to take this negative and bring it in the equation. So this negative right here, this sine, and this du are all going to make our dw. So this turns into the integral of dw over w, which is ln of the absolute value of w plus c. Now let's plug back in our functions. We have ln of the absolute value of cosine u plus c. Finally, u was e to the negative x, so it becomes ln cosine, and e to the negative x will never be negative, so we can drop the absolute value sign. That graph never drops below the x-axis, so finally our answer is ln cosine e to the negative x. Now let's move on to another application of this, differential equations. There's a whole class of differential equations. This is just scratching the surface. You might have scratched the surface in Calculus 1 as well, and they go a bit deeper now. Finding the general solution of a differential equation. let's see, we have this equation, dy over dx equals 3 over 2 minus x. So basically, you're trying to find some function, y, right, that when you describe it or derive it with respect to x, you're going to get this function. So let's work backwards to figure out what that function is. First, let's multiply both sides by dx, right? So now you can see this is something we're used to. And this equal sign right here means that no matter what you do to the left side, as long as you do it to the right side, you should be fine because they are equal. So can't we just integrate this and integrate this? Well, the integral of 1 dy is just y. There's where the y comes from. On the right side, this turns into 3, and I guess we should do a u sub. U is equal to 2 minus x, and du is equal to dx. So as you get better with this, you could just recognize that it's just going to become 3 ln of the absolute value of, oh, you know what? Du is negative dx because there's a coefficient negative in front. So that means we need a negative inside, so there's going to be a negative out front. So y is actually negative 3 ln of u, and u was 2 minus x. Let's check that real quick. Let's take the derivative of y with respect to x, like we started with. So when we take the derivative, d over dx, of both sides, we have dy over dx equals, that negative 3 is going to come out of the derivative, and then we just have the derivative of ln of 2 minus x. Well, that just becomes u prime over u. So the 2 minus x stays on the bottom, and u prime comes on top. The negative cancels the negative. You have dy over dx is 3 over 2 minus x, which is what we started with. So the answer was indeed y equals negative 3 ln of the absolute value of 2 minus x. And when you integrate both of these, you do have some constant, and we're going to be able to figure out what that constant is. So like, this one would produce some constant 1, right? And this one would produce some constant 2. And the sum of those constants that becomes c is just a new constant, so we can just continue to call it c. And we'll actually be able to figure out what that constant is with an initial condition. That's called finding the particular solution, which we will do in this video. But first, let's get a little bit more practice with this. We're going to multiply both sides by dx like always, and then integrate both sides. Now we have y plus that c1, it's a good habit to get into, is equal to the integral, let's split this into two integrals. It's going to be x over x, which is 1 dx, minus the integral of 2 over x dx. So you can see the natural log part is going to come from this one. And so we get y plus c1 equals the integral of 1 with respect to x is x, and the integral of 2 over x is 2 natural log of x, and that c2 from both of those integrals. Finally, we can gather all the c's to one side to just call that c. It's going to be x minus 2 ln x plus c. That is our final answer. Okay, now let's move on to something a bit harder. They give us some initial conditions, right? They tell you that when f prime of 1, the function will equal 1. Or, I'm sorry, when you plug in 1 into the derivative, you're going to get 1, and when you plug in 1 into the actual function, you're going to get 1. So that's going to allow us to solve for c. What they did is they gave us a second derivative. We know that when we integrate this second derivative, we're going to get the first derivative and some constant. We're going to be able to figure out what that constant is using this initial condition. So let's integrate the second derivative, 2 over x squared, with respect to x. With respect to x, and we're going to get, well, let's see, that's 2x to the negative 2. So we're going to add 1 to the exponent and divide by that new number. 2 divided by negative 1 is just negative 2. and there's some constant, and we could also rewrite that as negative 2 over x. Let's see, when you take the derivative of this, it's going to increase the power of x to 2 and bring another negative out front. So this is the correct derivative plus c. So what that tells me is that f prime of x equals negative 2 over x plus c. But if f prime of 1 equals 1, well, let's figure out what f prime of 1 is. Let's plug in 1 into our function. It's negative 2 over 1 plus c. So f prime of 1 is negative 2 plus c, and supposedly that equals 1. Do you see how we're going to be able to figure out what c is? We can just add 2 to both sides to figure out that c is 3, because these cancel. Okay, so that means that this c right here is 3. So we can start again. Now we have a new, let me start with a new color. We have f prime of x. F prime of x is negative 2 over x plus c, but we just proved that c was 3. And now what we want is f of x. That was our goal this whole time. And we know f of x is just the integral of f prime of x with respect to x. So we're going to integrate negative 2x and that 3 with respect to x. And we're going to be able to figure out what the c from this integral, the constant from this integral, is as well. So when you integrate negative 2 over x, you just get negative 2 ln of x. And when you integrate 3, you get 3x. And of course, you're going to get some constant. So this is what f of x is. F of x equals negative 2 ln of x plus 3x plus c. What they tell us is that f of 1 equals 1. Well, let's figure out what f of 1 is. F of 1 is negative 2 ln of 1 plus 3 times 1 plus c, and that is equal to 1. Well, ln of 1 is just 0, so that term drops out. We have 3 plus c equaling 1, so c equals negative 2. The final step is to just plug that back in here for c to get the answer. F of x equals negative 2 ln of x plus 3x minus 2. So with some integrations, we can figure out what those c's are to find a general solution. Okay. The last thing that we have to do are some definite integrals. So with definite integrals and ln, it's going to be the same process as we did with u sub. It's just sometimes, if you're not familiar with the natural log function, plugging in values into the natural log function, they can be hard to simplify. But let's see. With this function, what I see when I look at this integral, it's the integral of 0 to 2, I see an x squared minus 1, and then another minus 1. Those negative 1s become that negative 2. And the reason why I want to split up like that is because we're going to be able to rewrite this integral is 0 to 2. We can split it right here into two integrals. X squared minus 1 over x plus 1 plus the integral of negative 1 over x plus 1. As you can see, this one on the right is going to become the natural log function. Also, don't forget your dx's in the bounds. The reason why I chose to split it there, I strategically chose to split it there because we could rewrite this integral as a difference of squares, which means it can factor to a plus b, a minus b, and that will allow us to cancel these x plus 1 terms. So all of this right here just turns to x minus 1. The right side is going to stay 0 to 2 of negative 1 over x plus 1 dx. Right, so now when you're integrating x minus 1, you're going to get 1/2 x squared minus x. And we're going to evaluate that at 2 and 0. This one on the right is going to become the natural log of x plus 1, because even though we need a chain rule for this, the derivative of the inside here is just going to be 1, so we can skip the u sub. And then we're going to evaluate that at 2 and 0. So this part is what some people might consider hard, because sometimes ln can be tricky to simplify, but this one it's going to work out perfect. So let's plug in 2. 1/2 times 2 squared is just 2 minus 2. Well, that works out good. And then we're going to 0 minus 0. So all of this is just 0. Then we're subtracting, let's see, let's plug in 2. We get ln of 3 minus ln of 1. We know that ln of 1 is 0. This is 0. This is 0. So the final definite integral, the final area, just turns into negative ln of 3. And that is our final answer. Yes, area can be negative, because integral is just an area under a curve. Furthermore, it's going to be the same kind of process for this problem. So let's see. What I see when I look at this picture is I see a 1 over x times this quantity. And I like to see that because I also see an inside composite function here. So I'd like to get rid of this inside composite function with a u sub, u equal to 1 plus ln of x, right? And we have exactly that du, because the du is just the derivative of ln of x, which is 1 over x, and we have that. So this and this 1 over x make our du, right? So we're going to integrate 1 to e. We have u squared du. But these bounds here, these bounds right here, are bounds of x, right? So we have two options. We can either do the integral, plug back in our function of x, and then evaluate them at those x bounds, or what I prefer to do is to just plug those bounds into the u function as well to convert those x values into u values, because we have to evaluate if a function has a du and a function of u, these better be u bounds. So they're really not 1 and e. What they are is, let's see, when we plug in 1 into u, so u of 1, we get 1 plus ln of 1. ln of 1 is just 0. So u of 1 is 1. So that 1 could have stayed. Let's see what happens when we plug in e. When we plug in e, we get 1 plus ln e. ln has a base of e, though. ln is really a logarithm, right? It's a logarithm, the natural logarithm. It has a base of e. You should have learned that when a logarithm is evaluated at its base, that whole thing just turns to 1. So 1 plus 1 equals 2. So now our u bounds, the bounds that we're going to use, are instead going to be 1 and 2. And then we don't have to change it back to a function of x now. So we're going to integrate, let me just rewrite it, integrate 1 to 2 of u squared du, which is 1/3 u cubed, evaluated at 2 and 1. So it's going to be 8/3 minus 1/3. Finally, that's 7/3. So the natural log part of this problem was going to be changing those u bounds. If we had kept them as x bounds, we would have plugged back in this function right here, this function of x, and still had to evaluate them, or still had to evaluate it at those x values. So that's where the natural log part comes from. So that is how we integrate the natural log function.